Hello everyone, welcome to part 3 of designing green spaces. In this part we're going to be adding yet more parks to our scenario. The goals of this particular activity are to help students learn to balance two opposing constraints in a problem. Oftentimes real life problems, real life optimization problems, they have, more than one consideration that you're trying to do. You're trying to maximize something while minimizing another thing, or maximize two different things, but then you've got a cost to that. And so that there's opposing constraints in these optimization problems, and learning how to balance those two things to find a solution that sort of, meets things in the middle is a really important skill, both in math and in life. And then also, through this, we want to foster creative problem solving, because a lot of this, the solutions are not obvious. And so it just takes a lot of, sit down and play with the thing and see what works out. So let's get into it. Last time, we were building parks in this neighborhood grid, and we were only allowed to do 6. But now the city is going to increase our budget. It's going to let us spend more money. And the goal is to cover a certain percentage of neighborhoods. We want to get between 75 and 85% of neighborhoods. And because percentages are difficult for everyone, but especially middle schoolers, we have them in actual numbers. We want to get between 91 and 103 neighborhoods covered within a 10-minute walk of these parks, right? So only 18 to 30 will be missed. So we want to cover as many neighborhoods as we can, but parks are expensive. Each costs $1 million. We want to do this in the least expensive way possible, because the city is not going to want to spend any more money than it needs to, right? Okay, so we've got these two sort of opposing things. We want more coverage, we want more parks, but we don't want to do it too much because each park costs a lot of money. So we need to do, we balance these two things. We have to take both into consideration. So maybe let's play around with here are some possible solutions. So let's just take a look. Maybe some students have generated these solutions, and let's discuss them. Let's think about them, right? So I'm looking at these solutions, and immediately one pops out to me. Solution 1 pops out to me in particular, because it has quite a bit of parks. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 12 different parks on it, which is, I think, more than the other ones, which have, let's say, 9, 10, and 10. So solution 1 is a lot more parks, and there's a lot of overlap, right? There's a lot of this. We've got this overlap here. We've got a whole bunch of different places where they overlap. Maybe these parks could have been spread out a little bit better to cover the area a bit better, which is what solutions 2, 3, and 4 do. And they look pretty similar. It's not obvious which one is best. Solution 2 has 9 parks, so it's less expensive. But it looks like maybe there might be more neighborhoods that aren't covered. So in solution 2, there are 26 neighborhoods not covered, which is that within our threshold we want? We want 18 to 30 neighborhoods to be uncovered. So yes, that technically counts, but maybe we can do better. Solution 3, only 20 neighborhoods are not covered. And in solution 4, 18 neighborhoods are not covered. So it looks like if we count up the neighborhoods that aren't covered, this also gives us another metric. But then it's not obvious. Which is better? Should we do 9 parks with 26 neighborhoods uncovered? That's within parameters. Or maybe we can add 1 more park and get 8 more neighborhoods who are covered. Is that worth it? Should we do it? These are not obvious questions to answer, and these are very good considerations to bring up with your students.